lecture on acidity, and so today we're primarily covering that pKa range from 0 to 50, which will encompass all the weak acids. And those are going to be defined as the functional groups that you've learned in Module 1. So from about -10 or -15 to 0 on the pKa scale, those were the strong acids, which completely ionize in water. And so that sort of line at 0 pKa is where we have to start considering other things such as solvent. Because this is organic chemistry, we don't really run a lot of reactions with straight water. We use other organic molecules as solvents, which solubilize the starting materials. And so we're going to start talking about solvent properties and how they can be compatible with the reactions we want to run. So we have to think about, because solvent is another molecule, we just want it to sort of sit there and solubilize everything but do nothing else. And so if we're looking at the functional groups that we're familiar with when we're trying to do an acid-base reaction, we have to think about what base is going to be strong enough to act upon that pKa but not do anything to the solvent. So we really want to start controlling things in the reaction process. So we'll talk about how hybridization affects acidity in these functional groups, the nature of the elements, so C versus N versus O, and then what types of bases we need to think about. Any questions before we get started here? So we'll just briefly review on this slide. Again, strong acids, when put into water, will ionize to hydronium. So water was the leveling solvent. And hydronium is H3O+. It's used for many different purposes in organic chemistry. We'll eventually look at a couple of them as we start learning reactions. Again, the majority of the functional groups that you've learned are all weak acids. And you're familiar with like sodium hydroxide as a base. Sodium hydroxide really won't act upon a lot of these weak acids. So that necessitates we learn other bases that are stronger. And so it's our goal to understand how we can match the base strength to the pKa value so that we get a reaction to happen, and only on certain functional groups. So the strong acids were -15 to 0, 0 to 50. Those are the functional groups we learned. And one more thing to point out, that 0 to 50 region, so that's 50 pKa units. But remember, that's a log scale. And so when we start talking about the differences between two pKa's, the difference is really 10 to the n, where n is that difference. And so if you have a difference of 3, it's 10 to the 3, and so that's a factor of 1,000. So again, we applied that log function so we could deal with manageable numbers, but just keep in mind it's a log scale. So we'll start off with, these are the weak acids, and then from this table through the rest of the lecture, we'll talk about factors that influence acidity and how we choose bases to act on these functional groups. So in the column, first column here, these are all the functional groups that you learned. And so when you see that word, you want to think of that collection of atoms that makes up that functional group. So for example, a carboxylic acid, shown there, that's ethanoic acid. So we're talking about that H right there.
even though that molecule has, two unique sets of H. We're talking about the carboxylic acid H. And then the fourth column, pKa, that's how the table is arranged. So at the top are the stronger acids. So remember, the lower that pKa number, the stronger the acid. So carboxylic acids have a pKa of about 5. And then as you go down to the bottom, that's where you see alkanes. That's your typical CSP3H. And that sort of tops off the region there at 50. So these are stronger, and I'll just say weaker. And then the next column is the conjugate base that's formed of those acids. And then just some nomenclature of how you would name the conjugate base. So row 2 here is if you have an amine and it's protonated, that forms an ammonium salt. So notice that this is, I think, the only one that's bearing a positive charge. So its pK is about 10. When you deprotonate it, you get ammonia, and that's the only one there that is the conjugate base is neutral. For your module exams, you're free to use this table or your textbook or whatever, but eventually when you get to the final exam, the only thing you have is a pencil in your brain. So you want to have sort of an idea of where these functional groups lie on the pKa scale. And the most straightforward thing, I think, is, rather than trying to memorize 4.75, just round all of these to about the nearest 5. So 5, 10, 15, 20. That gives you a better sort of clarity on where these functional groups fall. So the third one is phenol. So that's an alcohol attached to a benzene ring. That's about 10. So that forms phenoxide. You'll notice some of these end in IDE. And in terms of chemical nomenclature, that's usually indicative of a negatively charged species. Water, when it's deprotonated, forms hydroxide. That pK is 14. Notice now your typical alcohol, say ethanol, that's around 16. The structures of alcohols sort of vary, so they're about 14 to 17, so they have a little range there, but 15 is a good value to keep in mind. And I think from here, sort of now in the next one, ketone, we're not talking about a hydrogen bonded to a heteroatom anymore. So it's a hydrogen bonded to a carbon. And so again, that's the new thing now, is those are considered acidic protons. So propanone is this molecule. So it's a 3-carbon ketone. It has one unique set of hydrogen. So the 2 methyl groups. So if you treated that with some base, that base would abstract that hydrogen. You would break that sigma bond, and now the carbon would be negatively charged. And so that is called a carbon anion, or carbanion. The other thing that's important is that base that deprotonated, it's still floating around, and now it's in its conjugate acid form. So we would balance the charge by saying the base is now plus. And so when we start talking about matching bases to weak acids, we're going to look at the pKa values of both acids. So on the reactant side, you have the acid. On the product side, you have the conjugate acid. We look up those two pKa values, see what the difference is, and see if what sort of equilibrium will be established. So then we have an ester. I'll draw some of these things out on later slides, but so, you're getting up to 20, 25 now. And again, as the number gets larger, the acid gets weaker. So alkynes, that's a C SPH hybridized carbon there. Hydrogen, so H2, that's 35. Notice the next one, ammonia. So ammonia is NH3. Notice the difference between that in the row 2 there, which was ammonium. So that was NH4. When you deprotonate ammonia, you get NH2 minus. And kind of something weird, N minus is called an amide base. But you learned in Module 1 that an amide is a carbonyl-containing functional group. So that's also called an amide. I don't know why, but you make sure you keep those two names clear based on the context in which you see them. Alkenes have C sp2H, and those are about 45, and then the alkanes with the sp3 hybridized carbon top it off at 50. And so again, that's where the functional groups lie, and really what we want to start figuring out is what base do we need to use to act upon those functional groups. For example, sodium hydroxide will not deprotonate an alkane. If you take any alkane plus sodium hydroxide, from now until the heat death of the universe, nothing will happen. It's that base is not strong enough to do that CH deprotonation. So the periodic trend for acidity. Remember that acidity, when we talk about that, we're also implicitly talking about basicity, so they're complementary to one another. And so in this table, we have C, N, O, and F. The electronegativity values from the periodic table, again, increase towards fluorine. And then here are just some simple examples of acids. So methane, ammonia, water, and HF. The next row is their pKa value. So methane is an alkane. That CH acidity is 50. Ammonia is an amine. It's about 40. Water is an alcohol. That should be 14. And then HF was 3.2. So again, as that pKa number decreases, the acid increases in strength. So if you remove a hydrogen from those molecules, you form the conjugate base. And notice that the conjugate base trend is opposite from the acid. So a weak acid has a very strong conjugate base. A strong acid has a weak conjugate base. So there's the inverse relationship between acidity and basicity. And so for any group, again, the groups are the vertical columns in the periodic table. As you go down the group, the acidity increases. Again, because you're sort of mismatching the size of the atoms at that point, the bonds become longer, therefore the existing bond is weaker, and the H atom is more acidic. Any questions at this point? So let's focus now for a little bit on CH acidity. And so this slide is showing you how the hybridization of the carbon atom affects the pKa value. So here's a molecule that we've seen before, gifratoxin, where we're going to observe that and validate it based on some functional groups that we see. And so let's just identify them. So HC, that's an alkyne. HB is an alkene. And then HA is an alkane. So really, when you're given a molecule, you're sort of looking at the minimum amount of atoms that make up that functional group. So when I say alkyne, there's that alkyne formula, and this is what we're looking for, this CSPH bond. And so the pKa of that HC is 25. For the alkene, CSP2, that pK is 44. And then for the alkane, SP3, that's 50. So I'm just identifying 3 of them. I mean, there's a lot of other alkane CHs in there, but for the purposes of comparison, I've just identified those 3. And again, what the pK value is telling you here, 25 is the strongest. That's the strongest acid. And the reason that hybridization affects acidity is based on this thing called %S character. And really what you do is for SP, there's an S orbital. So 1, and then there's 2 orbitals total. That gets you 50%. And because the S orbital is spherical and closer to the nucleus, the negative charge that's formed is better stabilized with more S character. So if we overall look at this molecule, the alcohol down there has a pK of 15. So no matter what base you treat this with, that OH will be deprotonated first. But if you were to add a second equivalent of a base, the alkyne hydrogen would be the next one that's deprotonated. So given any molecule, you need to identify all the functional groups, then go to the table and find the pKa values to rank their acidity. And that's going to tell you where the acid-base reaction will take place first, second, third, etc. So again, as we rank them, we said the alkyne was 25. The alkene was 44, and the alkane was 50. So I sort of model these questions after how the ACS exam is written, and they do a lot of these sort of most to least, least to most rankings. So in terms of that, if we use the numbers, so 25 is greater than 44, is greater than 50. So once we do that, you sort of just plug in what hydrogen it is. So HC is going to be the most acidic. So that'll eliminate choices B and C. Then HB, so that eliminates A, and then D is the correct response. So again, pay attention to how questions are phrased, and then if you see these greater than or less than symbols when ranking. So over the next couple slides, we're going to talk about acid-base reactions and how we draw the arrow in between. So for any acid-base reaction, is the product side favored? Is there some sort of equilibrium that's set up, or is there no reaction where the reactant side is favored? And the way that you do that is you identify the acid on both sides. So this acid is called phenol. So that's an alcohol with a pK of 10. On the product side, this is called cyclohexanol. And that has a pK of 16. So overall, the change in pKa is 10 to the 6. Because remember, that's a log scale. I think as a general rule, if the delta pKa is greater than 10 to the 5th, you can assume that it's going to favor the products. If the delta pKa is 10 to the 0, between 10 to the 0 and 10 to the 5th, that's when you start getting into this sort of equilibrium. And we'll talk about how you draw those different arrows on the next upcoming slides. So the reaction shown, it's asking us to draw the arrow. And when I was using the eye clickers, basically, you'd enter a string of digits to represent what the arrows were. But what we want to show is the movement of that hydrogen there from the phenol to the cyclohexanol. So phenol is acting as the acid, and then this negatively charged species is the base. So the base is going to abstract that hydrogen using a lone pair of electrons on that oxygen. So the arrow starts there. So in terms of the numbers, you would say like 5, 4. And then we have to break the OH bond. And so that would be 3-2. So I did that for many semesters, and it never really panned out the way I thought it would in terms of students understanding it, so I just kind of dropped it. But the start of the number is the start of the arrow, and where it's pointing is the arrowhead. So that shows you the transfer of that proton from the acid to the base. So there's what you'll need to add on your slides here. I think this H is probably missing on your slides. It's been 3 years and I still haven't corrected it. I tell myself after every lecture I will, but I never do. So we're using sodium hydroxide in both reactions. And now what we're comparing is the effect of resonance on acidity. If you look at the two acids, we have ethanoic acid and ethanol. Both of them have OH. The numbers in red are the pKa values. So the OH group in ethanoic acid, that pKa is 5. In ethanol, it's 16. The base is the same. So the question is, looking at these other two carbon atoms here, in ethanoic acid and in ethanol, the difference in acidity arises from that carbonyl group. So you have an sp2 hybridized carbon in a carbonyl group. Then you have just a regular sp3 hybridized carbon. The presence of that carbonyl group, notice it drops that acidity by a factor of 10 to the 11th. This is 10 to the 11th more times acidic. So when you treat with sodium hydroxide, that's the base. It's going to abstract that hydrogen. And now notice on the product side of both, you're forming water in both cases. And that has a pK of 14. And then the next thing to notice is the nature of the arrow in between. So this is a one-way arrow. And then this arrow is sort of back and forth. The reason we can claim to do that is the difference in pKa values for each reaction. So 14 minus 5, that's 10 to the 9th. 14 minus 16, if we use just the absolute value. So when you're sort of 5 or below, it sets up an equilibrium because the strength of the acids is so close to one another that this conjugate base can go ahead and deprotonate the water and go back that way. So if you had those ethanol plus sodium hydroxide, you actually have 4 things in the reaction. And that's really not ideal because you want to control how these things move further on in whatever reaction you're doing. So up here, sodium hydroxide will fully deprotonate that carboxylic acid to give you that and water. This will not go backwards because of that difference of 10 to the 9. And so the reason this is so much more stable is that that negative charge is stabilized by resonance. onto the other oxygen of the carboxylate group. Is there a question? Yeah.
So it doesn't matter which house and which, because if you do 14 minus 5 equals +9, then you do 14 minus 6 equals -2. So does it matter, like, whether it's positive or negative?
To a certain extent, you know, if you take the absolute value and it's sort of 5 or below, it's going to be back and forth. But if how do I want to do this? If this number over here, say if that was 25, that would then be negative, right? So at that point, it would matter. So again, two very different functional groups with the same base. Again, you're comparing the conjugate, or you're comparing the acid, the conjugate acid pKa values to help determine if the reaction moves forward, if it sets up some sort of equilibrium, or if it doesn't do anything at all. So some arrows as a review. A forward reaction that favors products is drawn one way. Equilibrium, where the side is not specified, sort of these half arrows of equal length. Equilibrium that favors more of the product. The longer arrow points towards the products. If the reactants are favored, you have the longer arrow pointing towards the reactant side. Resonance is this double-headed arrow. For arrow pushing, showing the movement of electrons, notice these two. See that? We call that a double-headed arrow. That means the movement of 2 electrons. This fishhook looking one-sided arrow, that's the movement of 1 electron. So it's subtle, but just pay attention. When we get to module 4, that's when we'll start using this fishhook arrow for single electron movement. And then this weird-looking arrow here, we'll talk about this more at the end of this semester. It's called retrosynthesis, where we take a molecule and then we think backwards to how can we arrive at simpler parts to ultimately make that molecule. So it's sort of like a blueprint arrow. But the different arrows, again, are telling you different things, so just pay attention to the context. So given the reaction, what is the most appropriate arrow to use? So the first thing we want to do is identify the acid on both sides. So there's a negatively charged carbon. That's going to be a base. We have an alcohol. The OH group is going to be an acid. On the product side, we have this negatively charged oxygen. That's called an alkoxide. That's going to be a base. And then we have this alkane, which is just CH bonds. That's going to be an acid. So again, that may seem a little weird to you, a CH bond being acidic. But the next thing we're going to do is, use the names of those functional groups in reference to the table we saw, find the pKa values of the two acids, and then compare or subtract the difference. So we'll say the alcohol pKa was about 15. The alkane pKa was about 50. So if we subtract those two, so that gets us a difference of 35. And again, that's greater than, our sort of range of 5. And then from that, we would say the arrow we want to write between them is A. The carbanion will abstract that H. You break the OH bond, and it will go favor the products 100%. So to phrase that another way, if you started with an alkane and you tried to use this base to deprotonate a CH bond, it would never happen. That base is not strong enough to deprotonate that. So that then begs the question, what types of bases are strong enough to do that sort of reaction? And so that's ultimately where we're going in this lecture. So to put things into context again, because you'll sort of see the same functional group over and over, OH, NH, CH. What factors then affect the acidity? So if we have two alcohols here, both have OH. But then if you look at what's bonded to them, that really affects the acidity of the molecule. So phenol has a pK of 10, ethanol 16. So the phenol is much more acidic. So why is that? When you deprotonate phenol, the negative charge ends up on oxygen. And now, because it's bonded to that benzene ring, that negative charge can be delocalized through resonance. And so that's sort of sharing the misery, as it were. The other carbon atoms in that ring can bear some of that negative charge, so the oxygen's not as unhappy. And so here again is a resonance arrow. And then you can draw a couple more resonance forms for that. I'll let you do that in your notes. But when you deprotonate ethanol, the negative charge, it can't do anything. It's stuck on that oxygen. So there's no way to stabilize it. So the correct answer for this would be A. The conjugate base of phenol is resonance stabilized, whereas ethanol is not. So again, even though they both have OH, we have to look at other parts of the molecule to help rationalize why one is more acidic than the other. So this was an iClicker question. you'd see the molecule show up on your phone, and then you'd press which hydrogen was most acidic. Again, the logic here is you have to identify all the unique sets of hydrogen, classify them to their functional groups, rank the pKa's, and then figure out which one is the most acidic. In general, hydrogen atoms bonded to heteroatoms are more acidic. So you have two alcohols here. This one is part of phenol because it's bonded to the aromatic ring. And then this is your normal, secondary type of alcohol. So we know that those alcohols are definitely more acidic than any other sort of CH bond. And then of those two, the OH of the phenol is going to be the most acidic. So put another way, if you treat this molecule with one equivalent of base, the OH of the phenol gets deprotonated first. And so, again, why is that important? So you can, as we say in research, you can derivatize that oxygen in preference to that secondary alcohol oxygen. So let me do some highlighting here. So HA and HB are bonded to carbon. C and D are bonded to oxygen. And so it asks, why are OH bonds more acidic than CH bonds? And sort of the simplest explanation is that, as we move across the periodic table, electronegativity increases. So putting the negative charge on oxygen is more stabilized due to electronegativity. So we would say A is the best response for that. So again, in general, anything that can stabilize the negative charge, ultimately increases the acidity. So the structure on the left is morphine, and that's isolated from the poppy plant. So if you're interested in med school, pharmacy, or any sort of health profession, a common way to treat things is through drugs. Obviously, if you go to a doctor, they're going to give you a drug first before they decide to cut you open, right? That's more evasive, it's more expensive. So the therapeutic indication is sort of the area in which that drug acts. And so morphine is an analgesic, which means pain relief. So it's in the class of compounds called opioids. And if you sort of pay attention to the media, we're in an opioid crisis. Opioids are typically overprescribed, and they're addictive. Everyone in this room, it doesn't matter color, creed, social status, what. If you take enough opioid, you will get addicted. It's just brain chemistry. There's no stopping it. So morphine, it's what we call a natural product. And if you're into biology, botany, that sort of thing, you can ask, why does this plant produce that thing to begin with? So maybe it's by some higher order design, whatever deity you believe in. made this plant produce that so humans could use it for pain relief. But typically morphine is sort of the benchmark for painkillers. But what if, you're in like end stage cancer and just morphine ain't cutting it? And so that's where synthetic organic chemistry comes in, where we make derivatives of things. And derivatives are just adding functional groups to an existing skeleton. And then you test it. Is it more potent? Is it less potent? Typically what scientists want to do is increase potency, but then decrease dose. You don't want to take a gram of something, right? Maybe on an antibiotic, you got to take like 500 milligrams. But that's a pretty big dose. Most doses of things like birth control, I think, is like 0.3 milligrams or something. So you want the smallest dose possible with the most potency. So as shown here, if you take the morphine skeleton and you do some chemical reactions identified at sites 1, 2, and 3, if you look at site 1, that alkane has become a tertiary alcohol. The secondary alcohol at position 2 has become a ketone. And then position 3, the OH has now become an ether. And so this molecule is called OxyContin, and it's 2 times the strength of morphine. What's interesting, though, is have you ever heard the word nociception? Like the perception of pain. So even though we're all humans, we all perceive pain differently, right? I mean, there's a certain response time if you put your finger on the stove. You don't feel it right away. It takes a little bit, right? It's like 80 nanoseconds or something before you're like, hey, I'm burning my finger here, and then you go, ow. But the sort of quantity of pain that you feel, it varies from person to person. So even though this is 2 times the strength of morphine, you can start making other derivatives of this that are more potent. So heroin is a derivative of the morphine skeleton. Forgetting the name of it, but there's all these other sort of derivatives of this class. And the reason that, people become heroin addicts is typically they can't get the prescriptions for this anymore. And so heroin it's easier to get on the streets. And so that's sort of like a downward slide. But these molecules are important for healthcare reasons, and outside of the natural products, they're pretty much all synthetic materials. So in the last little bit here, we're going to discuss trends. So with the ultimate goal that we can start matching what base we need to use to act upon a certain functional group. So we have 4 functional groups here, and it's asking which of the following acids has the weakest conjugate base. The first thing we'll do, let's just identify the main functional group. So A is a carboxylic acid. B is an alcohol. C is a ketone. And then D is an alkane. So it says, which has the weakest conjugate base? So it's really asking you which one of these is the strongest acid. So now that we've named them, we go back to the chart, we could just write the pK numbers below. Carboxylic acid was about 5. Alcohol is about 15. Ketone about 20. And then alkane 50. So if you run the acid-base reaction, you deprotonate the functional group, you get the conjugate base. The weakest conjugate base is going to be this one, A, because that's the strongest acid. So in preview of the next slide, which is which one of these has the strongest conjugate base, since the alkane is the weakest acid, it has the strongest conjugate base. So again, that's called a carbanion, a negatively charged carbon. And hopefully you can sort of realize why that's the strongest base. If you have a negatively charged carbon, like it's really unhappy. It's like if you haven't eaten lunch, you're angry, you want to go get your Chick-fil-A sandwich and get satiated. That's what that base wants to do. It wants to react with some acid so it gets back to a neutral carbon. So again, there's the slide. Just keep in mind the inverse relationship between acidity and basicity. So strong acids form weak conjugate bases. Weak acids form strong conjugate bases. So we previewed this topic last time, the inductive effect. So the tug of war with the rope, you have two sides tugging on each other. We saw that for this series of again, a carboxylic acid is just CO2H. It's always at the end of the chain. So CO2H. What is affecting the acidity of that OH is the stuff that's bonded to the CO2H group. And we saw that when that carbon next door has 3 fluorines, it's the most acidic. When it has 3 hydrogens, that's sort of your normal carboxylic acid value of a pK of 5. So as you substitute these F atoms in there, they're, again, tugging through the sigma bond network. So I'll highlight those in blue because that atom is electronegative. We say it's delta minus. It's helping to weaken the OH bond. And then as you add more, it's not a linearly additive effect, but it's increasing the acidity quite a bit. So if I can preview some nomenclature for you. We know that a CO double bond is called the carbonyl group. The carbon atom bonded to that is called the alpha position. And then you just follow the Greek alphabet, alpha, beta, gamma, alpha, beta, gamma, delta. So notice in this trend, the location of that fluorine atom, as it gets further and further away from the carbonyl, the tug-of-war effect lessens. So it's like, you know, the two people closest on opposite ends of tug-of-war probably feel the physics more of that rope than the schlubs at the end of the thing. They're just kind of hanging on and not doing any work. So as that atom moves further and further away, you know, this acid to the right, you know, that pK is probably 5 because that fluorine isn't affecting it as much. Any questions? So we have 3 minutes. I don't want to rip you off. I know you're paying a lot of money for this class, but I don't really want to start this whole next topic and sort of chop it at a weird breaking point. So I think we'll stop here today. We'll finish up acidity on Wednesday. And then do we have class Friday? So no class Friday. We'll finish acidity Wednesday, and then we'll start conformational analysis as well.